Gauss was a lonely child. Sure, he was gifted, a genius in math and physics, but that didn't automatically win him friends. To be precise, it rather worked against him being the cool kid on the block, quite to his confusion. As he grew older, his family became more and more concerned about his well-being, until one day they decided that it was time for him to marry, and thereby finally find some company. Gauss wasn't very pleased about this though, as he viewed himself as being independent, only distributed over the normal space he needed as a bachelor. One day it knocked on his door.
"Hello, boy,"
his mom said gently.
"I think we found the ideal match for you. It's a very wealthy family, and rumors say their wealth still grows exponentially," she said with a wink.
Exponentially? Gauss asked himself. How is that even possible? But then again, he always thought of some part in him being exponential as well. His mother just continued talking.
"We just have to close the marriage contract and you will be in good hands."
She pulled out a stack of documents.
"You just have to help me a little with the math, boy. The Exponential family is quite picky and all their new members must fit in."
Gauss looked at the marriage contract and instantly became excited as formulas were looking back at him. "Don't worry, Mom," he said, smiling. "Don't you worry about me not fitting in." And so he explained to her how he could fit into the wealthy Exponential family. So, this is the distribution of the Exponential family. It's a probability distribution for the random variable x that depends on natural parameters. These natural parameters are called eta, and they can be seen as a vector, which means there can be more than one parameter that is characterizing the distribution. This will become important later, and means for now that we're dealing with a scalar. The exponential family is composed of several factors. The first one is h of x, which is the function of the data itself. The second one is the function g, that only depends on the natural parameter eta of the distribution. Lastly, you have the exponential part, and in there you have a mixing of the natural parameters and the function u, that again depends on the data itself. Next, we take a look at the Gaussian distribution, also known as the normal distribution. It's characterized by two parameters. The first one is the standard deviation sigma, which is a measure of the amount of variation in our data. The smaller the sigma, the tighter is the distribution. The larger the sigma, the more shallow is the distribution. The standard deviation is in the normalization coefficient of the Gaussian distribution, which is the term before the exponent, and it occurs in the exponent. There, it is used to scale the distance measure x mu, which is the distance that we observe between the data and the mu. Therefore, the distribution is centered in respect to mu, and mu is defining the center of the distribution. So, the Gaussian distribution is dependent on the parameter sigma and mu. The question is, how do we transfer these parameters into the natural parameter eta, so that Gauss can marry into the exponential family? When we compare the Gaussian distribution and the exponential family, we instantly see a common feature. They both have an exponential function. So, we define the exponent of eta times u of x as the exponent of -1 divided by 2 sigma squared times x minus mu squared. Taking a closer look at the last term, we see a binomial formula. Rewriting this binomial formula leads to the term x squared minus 2x mu plus mu squared. Multiplying this term with the -1 divided by 2 sigma squared leads to the following term. Minus x squared divided by 2 sigma squared plus 2x mu divided by 2 sigma squared. The 2's cancel each other out. Minus mu squared divided by 2 sigma squared. Having formed this new term, let's look again at our exponent of the exponential family. Because eta and u of x are vectors, we can write them as the sum of k equals 1 up to m, consisting of eta k times uk of x. We can also write this as eta 1 times u1 of x plus ... plus eta m times um of x. Comparing our two new formulas, one of the Gaussian distribution and one of the exponential family, we begin to see some patterns. If we set m to 3, we have the term eta 1 times u1 of x plus eta 2 times u2 of x plus eta 3 times u3 of x. This is the same pattern that we have in our Gaussian distribution. Thus, we can define eta times u of x as minus x squared divided by 2 sigma squared plus x mu divided by sigma squared plus minus mu squared divided by 2 sigma squared. We see now why it is important that eta and u are both vectors. The vector eta consists of eta 1, eta 2 and eta 3. Eta 1 equals 1 divided by 2 sigma squared, eta 2 equals mu divided by sigma squared, and eta 3 equals mu squared divided by 2 sigma squared. The vector u of x consists of u1 of x, u2 of x, and u3 of x. u1 of x equals minus x squared, u2 of x equals x, and u3 of x equals negative 1. So far, this looks pretty great, but the problem is, the vectors of the exponential family eta and u of x are three-dimensional, while the Gaussian distribution has only 2 degrees of freedom, sigma and mu. To fix this, we will try to reduce eta to a 2-dimensional vector. Luckily for us, eta 3 times u of x is independent of our data x, so we can extract it from the exponent and include it in the normalization coefficient g of eta that is outside of our exponent. Okay, let's pause for a second and look at what we've done so far. In the first step, we found a similarity between the exponential family and the Gaussian distribution, namely the exponent. In the second step, we rewrote both formulas and matched the natural parameter eta for the exponential family to the parameters sigma and mu of the Gaussian distribution. While doing that, we discovered that eta and u of x are mapped as three-dimensional vectors, although the Gaussian distribution has only 2 degrees of freedom, so we extracted eta 3 times u3 of x from our exponent. How does this look now? Let's look at the whole distribution of the exponential family again. So far, we only cared about the exponent eta times u of x. By extracting eta 3 times u3 of x, aka mu squared divided by 2 sigma squared times negative 1, we now have the vectors in the exponent that we were looking for. Eta is equal to eta 1 and eta 2, which are equal to 1 divided by 2 sigma squared and mu divided by sigma squared. U of x is equal to u1 of x and u2 of x, which are equal to minus x squared and x. Now let's look at the term in front of the exponent. We know vaguely that h of x and g of eta somehow have to match the Gaussian term 1 divided by 2 times pi times sigma squared to the power of a half. We remember that h of x is a function of the data itself, and because the Gaussian term is in no form dependent on x, we can simply set it to a constant. H of x equals 1 divided by pi to the power of a half. That leaves g of eta, which at the moment is defined as 1 divided by 2 times sigma squared to the power of a half, times the exponent of minus mu squared divided by 2 sigma squared. Although this might seem like a solution, g is now dependent on the parameters sigma and mu. In the distribution of the exponential family, however, it must be dependent on a natural parameter eta. In the first steps, we showed that the natural parameter eta is a vector consisting of eta 1 and eta 2. That means that we now have to define g of eta as g of eta 1 and eta 2. We first define g of eta 1 and eta 2 as 1 divided by 2 times sigma squared to the power of a half times the exponential of minus mu squared divided by 2 sigma squared. We know that eta 1 equals 1 divided by 2 sigma squared and eta 2 equals mu divided by sigma squared. Again, a pattern is visible. 1 divided by 2 sigma squared to the power of a half equals eta 1 to the power of a half. Nice! We have already rewritten the first part of g in dependence to eta. Let's turn our attention to the second part. It is the exponential form that we extracted from the exponent. The exponential of minus mu squared divided by 2 sigma squared, let's define it as g dash of eta 1 and eta 2. Let's look at these three terms very intensely now. Eta 1 equals 1 divided by 2 sigma squared. Eta 2 equals mu divided by sigma squared. And g dash of eta 1 and eta 2 equals the exponential of minus mu squared divided by 2 sigma squared.
Look at them, Mom. Look! Huh? Don't you see? No? Okay, look.
If we square eta 2, we get mu squared divided by sigma to the power of 4, which we can rewrite as mu squared divided by 2 sigma squared times 2 divided by sigma squared. Now, if we divide 1 by 4 times eta 1, we get sigma squared divided by 2. We simply divide eta 2 squared by 4 eta 1, which equals mu squared divided by 2 sigma squared times 2 divided by sigma squared, divided by 4 times 1 divided by 2 sigma squared. This results in the term mu squared divided by 2 sigma squared times 2 divided by sigma squared times 2 sigma squared divided by 4. The 2 times 2 in the numerator cancels out the 4 in the denominator. Also, the sigma squareds cancel each other out, so that we're left with mu squared divided by 2 sigma squared. Now, we just put a minus in front of it and tada! We get the term minus mu squared divided by 2 sigma squared. Thus, minus eta 2 squared divided by 4 times eta equals minus mu squared divided by 2 sigma squared. If we put our new term into the exponent, we get g dash of eta 1 and eta 2. Multiplying that with the first part of our g of eta, eta to the power of a half, we get a final result for g of eta 1 and eta 2. G of eta 1 and eta 2 equals eta to the power of a half times exponential of minus eta 2 squared divided by 4 eta 1. H of x equals 1 divided by pi to the power of a half. Eta equals eta 1 and eta 2, which equals 1 divided by 2 sigma squared and mu divided by sigma squared. U of x equals u1 of x and u2 of x, which equal minus x squared and x. I'm really glad, son, because this means that from now on your wife has to listen to all of this.